Everyone, this is the part 3 of our linear regression with R series. In this series, we are going to take a look at variable transformation. So the purpose of variable transformation is to make extremely right-skewed or left-skewed data appear normally distributed. Let's first check the distribution of our numeric variables that we have selected. These include cadmium, zinc, and OM, which stands for organic matters. The other two variables that we selected from the previous two sections are FFREQ and line. These two predictors are categorical. FFREQ represent the flooding frequency and has level 0 and 1, and the line measures whether there's line present and is also has level 0 and 1. Let's first load the data into our console and omit all the missing values. We then select the 5 variables plus our response variable lead, and we build the linear model and we present the summary of this linear model. We can see that the multiple R square is still 0.95% with the adjusted R square of 0.95. We first test the distribution of our residuals and distribution of our selected numeric variables to determine if we need to do any variable transformation. We plot the distribution of our residuals by calling the function QQ norm. And if the residuals closely adhere to this red line, this means that they are normally distributed, which further proves the R linear model is valid. However, from our QQ norm plot, we can see that the residuals do not adhere to the red plot here and here. This means that variable transformation is necessary. Let's first take a look at the 3 variables that we selected. They are numerical. The first one is cadmium, second one is zinc, and the third one is OM. Plotting the density plot, we can see that both zinc and cadmium has a right skew distribution. This can be seen by a long tail over here. However, if we take a look at OM, we can see that it's approximately normally distributed. So we don't need to worry about that. There are 2 ways to solve data that's not normally distributed. We can either take the square root or take the log. Let's conduct these variable transformations and then plot the distribution to see which one is more appropriate in our case. Here, I took the log of cadmium, took a log of zinc, and appended that into the data select data frame that we constructed at the beginning of the section. I've also taken the square root of both cadmium and zinc. Now let's plot the density plot for all of the 4 new variables that we just created. Here we can see that log seems to be a more appropriate variable transformation method in this case because it's approximately normally distributed. But square root, we can see it's still kind of rightly skewed. So we would use log in this case. We should also check our response variable's distribution. In this case, our response variable is lead, so let's plot the density plot of lead. We can see that it's also rightly skewed. So let's take the log as well and see if it makes the distribution more normal. And it does. Now our distribution of each of the numeric variables are more normal. Let's try to build a model using the newly transformed variables. We do that by building a model using cadmium, log, zinc, log, the organic matter variable that we did not touch, the two categorical variables FF, and line. Also, with our transform, the response variable is our transformed lead variable. Let's take a look at the summary of our newly created model 2. You can see that, interestingly, the multiple R-squared decreased slightly from 0.956 to now it's 0.954. Oh, it's 0.959 to 0.954. However, when we construct the distribution of our residual now, we can see that it closely follows the red line, meaning that our residual is much more normally distributed. This means the model that we have now is more valid than the model we have in the beginning of this section. If we're able to sacrifice such a small drop in our R-squared to achieve a more valid model, it is more desired.